In the humid morning of August 9, 1945, on the grounds of the Sagami Army Arsenal southwest of Tokyo, a group of Japanese engineers stood before a machine they had studied for years, but never truly understood. Before them sat an American M4A3 Sherman tank, captured weeks earlier in the chaos of Okinawa's final collapse. Its olive-drab paint was scarred by shrapnel and mud. Its tracks showed wear from Pacific volcanic soil. But its engine, that 500-horsepower Ford GAA V8, idled with a steady, almost mechanical serenity that unnerved every man present. They had been told to evaluate it, to measure it, to understand why this tank, supposedly inferior to Japan's own designs, had crushed imperial forces across every Pacific island where steel met steel. What they would discover over the next 72 hours would not merely be technical data. It would be a revelation about the nature of industrial warfare itself, and a painful mirror reflecting how far Japan had fallen behind. The Sherman had arrived at Sagami under heavy guard, towed by recovery vehicles after American forces abandoned several damaged tanks during the final Okinawa mop-up operations. Most were wrecks, but this one, number 2-30647, had suffered only track damage and minor hull hits. Its crew had dismounted under fire, but they hadn't sabotaged it. Perhaps they knew the war was ending. Perhaps they simply ran out of time. Either way, the Japanese now possessed the most intact example of American armor they had ever captured. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. For 3 years, Japanese tank crews had faced Shermans in the jungles of Guadalcanal, the swamps of Burma, the volcanic ash of Iwo Jima, and the sugarcane fields of the Philippines. Each time, the result was the same. Japanese tanks, outgunned and outmaneuvered, were destroyed with brutal efficiency. The Type 97 Chiha, Japan's most common medium tank, mounted a short-barreled 57mm gun that could barely penetrate a Sherman's frontal armor. Its own armor, just 25mm at its thickest, offered no protection against the Sherman's 75mm cannon. In tank versus tank engagements, survival rates for Japanese crews were abysmal. At the Battle of the Philippine Sea in June 1944, American Shermans destroyed over 40 Japanese tanks in a single day without losing one of their own. Reports from the field described American tanks advancing through concentrated anti-tank fire, absorbing hits, and continuing forward as if unstoppable. Desperate Japanese infantry resorted to suicide attacks, strapping explosives to their bodies and throwing themselves beneath Sherman tracks. It worked sometimes, but at horrific cost. By mid-1945, Japanese tank doctrine had effectively collapsed. Remaining armor was dug into static defensive positions, used as pillboxes rather than mobile weapons. Crews were told to expect death. Command staff spoke openly of the Sherman's dominance, though few understood why. Captured technical manuals provided specifications, but numbers on paper explained nothing about how the Sherman performed in the field, how it endured month after month of continuous combat without breaking down, how its crews could fight all day in tropical heat without mechanical failure. Now, standing before an actual Sherman, Japan's top military engineers had a chance to answer those questions. The team assembled at Sagami represented the best talent Japan had left. Most were veterans of the Technical Research Institute, men who had designed the Chi-Ha, the Type 3 Chi-Nu, and the experimental Type 4 Chi-2. They understood armor design. They knew engine theory, but they also knew their own tanks were failing. Engines overheated, transmissions seized, cooling systems couldn't handle extended operation. Even Japan's newest designs, rushed into production in 1944, suffered chronic reliability issues. The Americans, by contrast, seemed to have mastered something Japan had not. Their tanks worked, day after day, mile after mile, battle after battle. That was the mystery the engineers needed to solve. The inspection began with the exterior. The Sherman's sloped frontal armor, 51mm thick at a 56-degree angle, provided effective protection equivalent to much thicker vertical plating. Japanese designers had known this principle for years, but manufacturing limitations forced them to use simpler, less effective armor layouts. The Americans, with their vast industrial capacity, could forge complex shapes without compromising production speed. Then came the tracks. Wide, robust, with a ground pressure lower than Japan's lighter tanks, the Sherman could traverse soft ground where Japanese tanks bogged down. Its suspension, a vertical volute spring system, was simple and durable. Japanese tanks used bell crank suspensions that required constant maintenance and often failed under stress. The Sherman's design prioritized reliability over theoretical performance, a philosophy Japan had never fully embraced. But it was when the engineers opened the engine compartment that the real shock began. The Ford GAA-58 sat before them like an artifact from another world. 8 cylinders arranged in a 90-degree V configuration, liquid-cooled. Aluminum block, 500 horsepower at 2,600 revolutions per minute. On paper, Japanese engineers had seen these numbers before. What they hadn't seen was the execution. The engine bay was immaculate. Every component was accessible. Filters, hoses, and electrical connections were logically arranged. Maintenance could be performed quickly, even under combat conditions. Japanese tanks, by contrast, had engines crammed into tight spaces, requiring hours of disassembly to reach critical parts. The Americans had designed for field repair. Japan had designed for factory perfection. They started the engine. It caught immediately, settling into a deep, steady rumble. The engineers monitored temperatures, pressures, and vibrations. Everything remained stable. They let it idle for an hour. No overheating. They increased throttle. The engine responded smoothly, linearly. Japanese tank engines, even when new, exhibited rough idle and uneven power curves. This American engine felt like an industrial machine, not a temperamental prototype. Then came the real test. They would drive it, under load, in heat, for as long as fuel permitted. If the Sherman's reputation was built on reliability, they would measure that reliability with precision. A test course was prepared, simulating combat conditions, rough terrain, steep inclines, prolonged high-speed runs. The engineers would push the Sherman until something failed, or until they ran out of questions. Over the next 12 hours, the Sherman covered over 60 kilometers. It climbed hills, it traversed mud pits, it accelerated, braked, turned, and reversed repeatedly. The engine temperature never exceeded normal operating range. The cooling system, a pair of large radiators with mechanically driven fans, maintained consistent coolant flow even under maximum load. Japanese engineers watched the temperature gauges with something approaching disbelief. Their own tanks overheated within 30 minutes of sustained operation. Crews in the Pacific had learned to stop every 20 minutes to let engines cool, a vulnerability American forces ruthlessly exploited. During the Peleliu campaign in September 1944, Japanese tanks attempting counterattacks were caught immobilized, engines overheated, and destroyed by American artillery before they could restart. The Sherman suffered no such weakness. The secret, the engineers realized, lay not in revolutionary technology, but in engineering discipline. The Ford GAA's cooling system was oversized, deliberately built with excess capacity to handle worst-case scenarios. The radiators were larger than necessary for normal operation, ensuring adequate cooling even when air intake was partially blocked by mud or debris. The thermostat maintained optimal temperature automatically, requiring no crew intervention. Japanese designers, constrained by limited materials and manufacturing capacity, had built cooling systems sized for theoretical efficiency, not practical reliability. When conditions exceeded design parameters, which they always did in combat, Japanese engines failed. American engineers had anticipated failure modes and designed systems to prevent them. The transmission revealed similar philosophy. The Sherman's synchromesh gearbox allowed smooth shifting under load. Japanese tanks used crash gearboxes requiring double clutching and precise timing, skills that degraded under combat stress. Inexperienced drivers rushed through abbreviated training programs as the war dragged on, often stripped gears or stalled engines. The Sherman's transmission forgave mistakes. It was designed for ordinary soldiers, not experts. Even the fuel system demonstrated American pragmaticity. The Sherman ran on standard 80-octane gasoline, the same fuel used by trucks and jeeps throughout the US military. Logistics were simplified, supply lines were streamlined. Japanese tanks required specialized aviation fuel, chronically scarce by 1945. Tanks sat immobilized not because they were damaged, but because they had no fuel. The Americans had built their armor around available resources. Japan had designed machines for resources they didn't have. As the testing continued into the second day, patterns emerged. Every system in the Sherman reflected a design philosophy centered on one principle: sustained operational capability. The Americans didn't build the fastest tank, the most heavily armored tank, or the most powerfully armed tank. They built a tank that could fight today, tomorrow, and the day after that. A tank that could be repaired by mechanics with basic tools. A tank that could run on common fuel. A tank that wouldn't abandon its crew in the middle of battle because an engine seized or a transmission failed. Japanese doctrine, by contrast, had prioritized individual combat performance over endurance. The Type 3 Chi-Nu mounted a powerful 75mm gun capable of penetrating a Sherman's side armor, but its engine was unreliable. Its transmission was fragile. In the handful of engagements where Chi-Nus faced Shermans, initial shots often succeeded, but prolonged battles inevitably favored the Americans. When Japanese tanks broke down, they were abandoned. When Shermans broke down, they were repaired and returned to service. The most damning revelation came when engineers examined the Sherman's maintenance logs, found inside the tank's storage compartments. The vehicle had been in service for 11 months. It had participated in operations across Saipan, Leyte, and Okinawa. According to the logs, it had required only routine maintenance: oil changes, track adjustments, filter replacements, no major component failures, no engine rebuilds, no transmission overhauls. 11 months of combat, and the tank was still operationally sound. Japanese tanks rarely lasted 11 weeks in combat conditions before requiring depot-level repairs. The Type 97 Chiha's air-cooled diesel engine needed overhaul every 200 hours of operation. The Type 3 Chi-Nu's engine failed even more frequently. Maintenance crews spent more time repairing tanks than crews spent fighting in them. The Americans had somehow solved the sustainability problem that plagued every Japanese armored unit. The answer wasn't mysterious. It was industrial. The Ford GAA engine wasn't a hand-built masterpiece. It was a mass-produced component, manufactured by the tens of thousands in factories equipped with precision machinery and quality control systems Japan couldn't match. Every engine was identical, every part was interchangeable. When a Sherman needed an engine replacement, a new unit could be installed in hours, not weeks. Spare parts flooded the supply chain. American logistics assumed components would fail and prepared accordingly. Japan built tanks the way it built swords, carefully, individually, with craftsmanship that bordered on artistry. America built tanks the way it built cars, quickly, identically, with processes designed for mass production and easy repair. In a war of attrition, only one approach could win. By the third day of testing, the engineers had compiled a comprehensive technical report. It filled dozens of pages with measurements, diagrams, and analyses, but the conclusion could be summarized in a single, devastating sentence. Japan could not have built this tank. Not with the resources available. Not with the factories remaining. Not with the skilled labor depleted by years of war. The Sherman wasn't superior because of brilliant design. It was superior because it embodied an industrial system Japan had never possessed and could never replicate. The report reached Imperial General Headquarters in Tokyo on August 13, 1945. By then, the first atomic bomb had already fallen on Hiroshima. The second had devastated Nagasaki. The Soviet Union had declared war and invaded Manchuria. Japan's military leadership was fracturing between those advocating surrender and those demanding a final suicidal defense of the home islands. In that context, a technical report about an American tank seemed almost irrelevant. Yet the document circulated anyway, passing through the hands of engineers, staff officers, and logistics commanders who had spent years trying to understand why Japan's armored forces had failed so completely. What they read confirmed what many had suspected but few dared articulate. The war had been lost not on battlefields, but in factories. The Sherman tank was merely the most visible symbol of a deeper truth. America had mastered industrial warfare at a scale Japan never approached. Consider the numbers. Between 1942 and 1945, American factories produced 49,234 Sherman tanks. Variants included the M4, M4A1, M4A2, M4A3, M4A4, and dozens of specialized modifications. Production peaked in December 1943 at 2,000 units per month. Factories operated around the clock. Assembly lines ran with choreographed precision. Workers, many of them women who had never touched machinery before the war, were trained in weeks to perform complex manufacturing tasks. Japan, during the same period, produced approximately 6,300 tanks of all types. The vast majority were light tanks and tankettes, vehicles barely adequate for reconnaissance, let alone frontline combat. Medium tank production never exceeded 100 units per month, and most months fell far below that figure. By 1945, total monthly production across all Japanese factories had collapsed to fewer than 30 tanks. The disparity wasn't close, it was apocalyptic. The Sagami engineers understood this. Their report didn't simply describe the Sherman's technical features, it contextualized them within the industrial ecosystem that made such features possible. The Ford GAA engine, for instance, was manufactured at Ford's River Rouge plant in Michigan, a facility covering over 1,000 acres with its own steel mill, power plant, and railway system. At peak production, River Rouge employed 100,000 workers and produced one complete engine every 6 minutes. Japan had nothing comparable. Its largest tank factory, the Mitsubishi Heavy Industries plant in Tokyo, employed fewer than 5,000 workers and lacked modern machine tools. Precision boring equipment, essential for manufacturing engine cylinders to tight tolerances, had been imported from Germany before the war and couldn't be replaced after Allied blockades cut off trade routes. When those machines wore out or were damaged in air raids, production quality deteriorated rapidly. The Sherman's aluminum engine block exemplified the problem. Aluminum was lightweight, corrosion-resistant, and dissipated heat efficiently, ideal for high-performance engines. But aluminum production required massive amounts of electrical power. The United States, with its extensive hydroelectric infrastructure, produced over 900,000 tons of aluminum in 1943 alone. Japan, with limited electrical capacity and few bauxite deposits, produced less than 70,000 tons. Most of that went to aircraft production. Tanks received whatever remained, which meant cast iron, heavy, and thermally inefficient. Japanese engineers had tried to compensate through clever design. Air-cooled engines, like those used in the Type 97 Chiha, eliminated the need for radiators and coolant pumps, reducing weight and complexity. In theory, this was elegant. In practice, air-cooled engines struggled in tropical climates where ambient temperatures exceeded 35 degrees Celsius. Without liquid cooling, engine temperatures soared, oil broke down, and components wore rapidly. Crews learned to shut down engines frequently to prevent seizure, but this made tanks vulnerable and predictable. The Americans, with their abundant resources and industrial capacity, didn't need elegant solutions. They could afford to install oversized cooling systems, heavy radiators, and powerful pumps. They could afford to use liquid coolant mixed with antifreeze, ensuring consistent performance from Arctic tundra to Pacific jungles. They could afford redundancy, backup systems, and safety margins that Japanese designers could only dream about. This abundance extended beyond engines. The Sherman's electrical system used waterproof wiring harnesses with rubber insulation, protecting circuits from moisture and corrosion. Japanese tanks used cloth-wrapped wiring that deteriorated in humid environments, causing shorts and fires. The Sherman's fuel tanks were lined with self-sealing rubber, a technology requiring synthetic rubber production that Japan lacked. Japanese tanks used bare metal tanks that ruptured and ignited when hit, turning survivable damage into crew fatalities. Even small details revealed the gap. The Sherman's instrument panel featured clearly labeled gauges with luminous dials for night operation. Japanese tanks had minimal instrumentation, forcing crews to judge engine status by sound and feel. The Sherman's radio equipment was standardized across all models, enabling seamless communication between tanks, infantry, and artillery. Japanese tanks often had no radios at all, relying on flag signals or runners to coordinate movement, a system that collapsed under fire. By the time testing concluded at Sagami, the engineers had documented over 200 specific technical advantages the Sherman possessed. Some were major, like the engine's reliability. Others were minor, like the quality of the seat cushions or the effectiveness of the ventilation system. Cumulatively, they painted a picture of two nations operating at fundamentally different levels of industrial sophistication. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The psychological impact of these findings cannot be overstated. Many of the engineers at Sagami had dedicated their careers to armored vehicle design. They had studied foreign tanks, read technical journals, and designed what they believed were competitive machines. The Type 3 Chi-Nu, introduced in 1944, represented Japan's attempt to match Allied medium tanks. It mounted a 75mm gun comparable to the Sherman's. It had thicker frontal armor. On paper, it should have been competitive. But the Chi-Nu never worked properly. Its engine overheated constantly. Its transmission failed after minimal use. Only 166 were ever produced, and most never left Japan. The few that did see combat were destroyed quickly, not because their armor was inadequate or their guns ineffective, but because they broke down. Crews abandoned them not to enemy fire, but to mechanical failure. The engineers at Sagami knew this. They had received field reports. They had investigated the failures. Now, studying the Sherman, they understood why their designs had failed. It wasn't lack of talent. It wasn't poor design decisions. It was lack of resources, lack of manufacturing capability, and lack of time to develop mature, reliable systems. The Americans had spent the 1930s investing in industrial infrastructure, tooling factories, and training workers. When war came, they converted that infrastructure to military production with ruthless efficiency. Japan had spent the 1930s fighting in China, diverting resources to immediate conflicts rather than long-term industrial development. When war with America began, Japan was already behind and falling further back every month. One engineer, a veteran named Tomio Hara, who had worked on the Chiha's initial design in the late 1930s, wrote a personal addendum to the Sagami report. His words were not included in the official document, but they survived in private papers later discovered by historians. He wrote, "We built machines to win battles. They built machines to win wars. We designed for individual excellence. They designed for mass sustainability. We believed craftsmanship would triumph. They proved industry would prevail. We were not defeated by better soldiers or superior tactics. We were defeated by factories we could never build and resources we never possessed." Hara's assessment was accurate. The Sherman tank, for all its technical merits, was not an exceptional machine in isolation. It was a component of a larger system. That system included mines producing iron ore, smelters refining steel, factories forging parts, railways transporting materials, ports loading ships, supply depots distributing equipment, and mechanics repairing damage. Every Sherman represented hundreds of tons of raw materials, thousands of man-hours of labor, and a logistical network spanning oceans and continents. Japan had tried to compete without that system. It had tried to substitute willpower for industry, courage for resources, and tactical skill for strategic depth. Individual Japanese soldiers and tankers fought with extraordinary bravery. But bravery couldn't forge aluminum. Courage couldn't repair broken transmissions. Tactical brilliance couldn't produce the 500,000 gallons of fuel needed monthly to operate an armored division. The Sherman didn't just outfight Japanese tanks, it outlasted them. It was there when Japanese tanks weren't, operational when Japanese tanks broke down, supplied when Japanese tanks ran dry. After Japan's surrender on August 15, 1945, American occupation forces took control of military facilities across the home islands. Engineers from the U.S. Army's technical intelligence teams arrived at Sagami Arsenal within days. They found the captured Sherman still operational, sitting alongside detailed documentation of the Japanese tests. The American engineers were impressed by the thoroughness of the Japanese analysis, but unsurprised by the conclusions. One American officer, Captain Robert Morrison of the Army Ordnance Department, later wrote in his report, "The Japanese clearly understood what made the Sherman effective. Their technical documentation is excellent, but understanding and replicating are entirely different challenges. Even if they had possessed complete blueprints and unlimited time, they lacked the industrial base to manufacture such vehicles at scale. The war's outcome was determined by productive capacity, not battlefield tactics." Morrison's report included an interesting footnote. During interviews with captured Japanese tank crews, many expressed respect bordering on envy for the Sherman. They described it as comfortable, reliable, and forgiving of mistakes. One crew member, a corporal who had survived 3 tank battles, said through an interpreter, "Our tanks required constant attention. If you didn't monitor temperatures, if you didn't shift gears precisely, if you didn't maintain perfect mechanical sympathy, the tank would fail." The American tank, we heard, did not require such care. It worked even when treated roughly. That is not engineering. That is magic. It wasn't magic. It was standardization. It was quality control. It was designing for the 95th percentile of operator competence rather than the top 5%. It was building machines that ordinary soldiers, hastily trained and thrown into combat, could operate effectively. The Sherman's controls were simple and intuitive. Its maintenance procedures were documented in clear, illustrated manuals distributed to every crew. Its parts were numbered and catalogued so that mechanics could order replacements without specialized knowledge. Japanese tanks, by contrast, assumed skilled operators and experienced mechanics. They required frequent adjustment and careful handling. When Japan's veteran tankers were killed in the Philippines and Okinawa, replacements lacked the expertise to keep machines operational. Tanks broke down not because of design flaws, but because crews didn't know how to operate them properly. The Sherman tolerated ignorance. Japanese tanks punished it. This difference extended beyond armor. American infantry weapons, aircraft, ships, and vehicles all reflected the same design philosophy: reliability over performance, simplicity over sophistication, mass production over craftsmanship. The M1 Garand rifle was heavier than the Japanese Arisaka, but it never jammed and required minimal maintenance. The C-47 transport aircraft was slower than many contemporaries, but it could operate from crude airstrips and absorb tremendous damage. The Liberty ship was slow and unglamorous, but American shipyards built them faster than German submarines could sink them. Japan, constrained by limited resources, designed weapons optimized for theoretical performance. The Zero fighter was faster and more maneuverable than early American fighters, but it lacked armor and self-sealing fuel tanks. When American industry produced newer aircraft like the F-6F Hellcat and F-4U Corsair, the Zero became obsolete overnight. The Yamato battleship was the most powerful warship ever built, but it consumed fuel at such prodigious rates that it rarely left port, eventually sinking without firing its main guns at an enemy surface ship. Japan's Type 93 Long Lance torpedo was the best in the world, but by 1944, American radar and fire control systems made torpedo attacks suicidal. Excellence in individual weapon systems couldn't overcome systemic industrial inferiority. By 1945, this reality was undeniable. The Sagami report on the Sherman tank was merely one data point among thousands, demonstrating the same conclusion. Japan had entered a war it could not win against an opponent it could not match. In the years following the war, Japan's industrial transformation became one of the 20th century's most remarkable stories. The engineers who had studied the Sherman at Sagami, who had documented American manufacturing processes and design philosophies, became leaders in Japan's reconstruction. They applied lessons learned not to building tanks, but to building cars, motorcycles, and consumer electronics. Companies like Toyota, Honda, and Nissan were founded or revitalized by men who had worked in military production during the war. They understood that quality and reliability were not optional luxuries but essential requirements. They studied American manufacturing techniques, particularly those developed by American quality control experts like W. Edwards Deming, who found a more receptive audience in Japan than in his own country. The philosophy that made the Sherman tank successful, designing for reliability and ease of manufacture, became foundational to Japanese post-war industry. The Toyota production system, developed in the 1950s and 60s, emphasized eliminating waste, ensuring quality at every production stage, and empowering workers to stop production lines if defects were detected. These principles were direct descendants of the lessons Japanese engineers had learned studying American wartime manufacturing. By the 1980s, Japan had become an industrial superpower, known worldwide for producing reliable, high-quality products. Cars that ran for hundreds of thousands of miles without major repairs. Electronics that functioned flawlessly for decades. Motorcycles that combined performance with dependability. In a strange historical irony, Japan had become what America had been in 1945, the world standard for industrial excellence. The Sherman tank itself continued serving long after World War II ended. American forces used Shermans extensively in the Korean War, where their reliability proved valuable on mountainous terrain and in harsh winter conditions. Israel acquired hundreds of Shermans in the 1950s and 60s, upgrading them with more powerful guns and engines. These modified Shermans fought in the Six-Day War of 1967 and the Yom Kippur War of 1973, proving effective against more modern Soviet-designed tanks. Several nations continued operating Shermans into the 1980s. Paraguay used them in the Chaco War. Chile kept them in service until 1989. The last combat use of a Sherman occurred in 1991 during the Croatian War of Independence. Nearly 50 years after production ended, the design remained functional, a testament to the engineering principles that Japanese engineers had documented at Sagami Arsenal in 1945. Today, examples of the M4A3 Sherman, the same variant tested by Japanese engineers, are preserved in museums worldwide. The American Heritage Museum in Massachusetts maintains a fully operational M4A3 with the Ford GAA engine. The Tank Museum in Bovington, England, houses multiple Sherman variants. In Japan, the JGSDF Public Information Center displays an M4A3 alongside Japanese tanks from the same era, a silent comparison of two different approaches to armored warfare. The specific Sherman tested at Sagami Arsenal, number 230647, does not survive. It was likely scrapped during the post-war occupation as American forces consolidated captured equipment. But the report the Japanese engineers produced survived in archives, and when declassified decades later, it provided historians with a unique perspective on American military technology viewed through enemy eyes. Reading that report today, one is struck by its objectivity. The Japanese engineers didn't minimize American achievements or exaggerate Japanese capabilities. They documented reality with scientific precision, even when that reality was unflattering. They measured the gap between what they had built and what their opponent had fielded, and they reported that gap honestly. In doing so, they created a historical document of remarkable value, one that illuminates not just technical differences between tanks, but fundamental differences in industrial philosophy. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The Sherman tank's 500 horsepower engine that never overheated became more than a technical achievement. It became a symbol of how wars are truly won, not by individual acts of heroism or tactical brilliance, but by the unglamorous work of engineers designing reliable systems, factory workers manufacturing quality parts, and logisticians ensuring supplies reach the front. The Japanese engineers at Sagami understood this in August 1945, perhaps too late to change their nation's fate, but not too late to learn a lesson that would reshape their country's future. In mechanized warfare, sustainability defeats sophistication. Reliability conquers performance. A tank that works every day is worth more than a tank that performs brilliantly once then breaks down. These truths, written in steel and proven in blood across every theater of the Pacific War, were finally acknowledged by Japan's finest engineers as they stood before an American machine that embodied everything their own industry could not produce. The Ford GAA engine's steady rumble, its unwavering coolant temperature, its predictable power delivery. These were not merely technical specifications. They were the sound of industrial mastery, the temperature of strategic superiority, the rhythm of inevitable victory. Japan had fought valiantly, but America had manufactured victory, one reliable component at a time, and that difference, more than any battle or bombing campaign, determined the war's outcome.